Question 2. How do we know when to charge and discharge the community battery? So to explain the importance of knowing this, we are going to run through 2 scenarios. The first one being that we have perfect knowledge or real-time knowledge of the export coming from the households, the solar export, and their consumption. And then the second scenario where we don't know in real time the solar PV export and the consumption of the households in real time, and we are forced to rely on a forecast. For the case of scenario 1, in this case we have 2 households, household A and household B, and from around about 12 to 1 p.m, household B is exporting 2 kilowatt hours of energy from its PV solar system, and household A is exporting 4 kilowatt hours from around 1 till 2 p.m. And because we know exactly when the households are exporting power, we can time the charging of the community battery such that it is charged at the same time as when the households are exporting PV. And the same occurs for when the households are consuming energy in the evenings. So that 6 kilowatt hours of stored energy is exported at the same time that the 2 households are consuming in total 6 kilowatt hours of energy. So we match the export or the discharge of the battery to the consumption energy of the households. Okay, now how does this settle? So how do we calculate the revenue from the community battery and the settlement for each of the households under this scenario? So the cost to charge the community battery is 0 because it's all, when it's charging, it occurs at the same time that the households are exporting energy from their solar PV systems. And the revenue for the community battery at this time is 6 kilowatt hours times $2, which is arbitrary but useful for this example, which is $12. So the revenue for household A equates to 4/6 of the total revenue of the community battery, which is $8, or 4/6 of $12. And its cost of consumption is $6. So the net settlement for household A is positive $2. And for household B, its revenue from the community battery is 2/6 of $12, which is $4. And its cost of consumption is 6, so its net settlement is negative $2. Let's repeat this example for scenario 2, where we are working off a forecast and don't have real-time measurements of the solar PV export and consumption of households A and B. So we have the same solar PV export for households A and B, 2 kilowatt hours and 4 kilowatt hours. And the community battery has to rely on a prediction on what the solar PV export will be from these homes. And its prediction is different to what actually is exported, and it's predicted that a total of 2 kilowatt hours will be exported from 12 p.m. till 3 p.m. approximately. And so that means that there is a key discrepancy here where it is charging the battery 2 kilowatt hours in total from 2 p.m. till 3 p.m. when there is no solar PV export coming from the homes, and therefore this power comes from the grid. So this is going to have an impact on the revenue for the community battery. And then in the evening, luckily in this example, the prediction matches the consumption of the households. So there's no discrepancies there between when the community battery discharges, and when the households consume. So on to the settlement for this scenario. Under a forecast, when the community battery is using a forecast value for the solar PV export. So the cost to charge the community battery is not free. It costs 2 kilowatt hours times $2, which is $4. So the revenue for discharging the community battery is $12 minus the $4, so using a net value of $8. So for household A, its share of revenue is 4/6 of $8, which is $5.30, and its cost of consumption is still $6, which means the net settlement for household A is negative 70 cents. This is compared to $2 for scenario 1. And for household B, its revenue from the community battery is 2/6 of $8, which is $2.70. And it still has $6 as a cost of consumption, which means that the net settlement for household B under this scenario is negative $3.30 compared to a negative $2 in scenario 1.